Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergy GATE Preparation app from Google Play Store. The link is available in the description of video. Now, suppose we have a reservoir which is at a higher temperature than the atmosphere at a temperature of T1, and we have the atmosphere, the lowest temperature reservoir available as temperature TO or T naught. Okay. Now, if I want to know that how much maximum work I can extract from this heat transfer, because T1 is higher than TO or T naught, so that heat transfer can be used to extract some work, and we can do that by using a heat engine between these two reservoirs. If I want to know that what is the maximum amount of work that I can extract, very obviously I have to use a reversible engine here, and if I use an irreversible heat engine, then the work output will decrease. Basic things we already know about them. But tell me whether my selection of reversible or irreversible heat engine affect the arithmetic of Q1, W0, W out and Q2. What I want to say is that when this heat engine is reversible, let us say, then this W out is coming out to be 70 joule. 100 joule of heat is supplied, 70 joule of work we have got as the output. And here Q2 will be 30. Why 30? Because Q1 is equal to W out plus Q2 is true for this case. But what I want to ask, that tell me if I change this heat engine, if from reversible heat engine I make it a irreversible heat engine, then in that case also can I use this relation? Yes, I can definitely use this relation, because this is law of conservation of energy. Energy cannot be destroyed, it can only change its form, right or not? Here, if I use irreversible heat engine, what will happen? This work output may decrease. Maybe from 70 joule it will come out, it will come down to 60 joule, because due to irreversible heat engine, how much work can be extracted will decrease. The maximum work we get when heat engine is reversible, the Carnot engine, is going to give you the maximum value of work output, and that work output is also the available energy of this heat. If I want to know that how much is the available energy of this heat coming from this reservoir, then what should be the answer? The work output of reversible engine or Carnot engine, heat engine, right? That will give you the maximum work output possible, and maximum work out that you can extract from the heat is nothing but the available energy, right or not? So in this case, if I use irreversible heat engine, its work out will decrease. It will fall, let's say, at 60 joule. But in that case, this Q2 will also get modified. This Q2 will increase to how much? 40 joule, right or not? Because this balance has to be maintained. If out of 100 joule, 60 joule of work is being produced now, then heat rejected will be 40 joule. But this mathematics of conservation of energy, that it can never be destroyed. If 100 is coming, 60 gone there, 40 has to go down as Q2, because it cannot be destroyed. You cannot have that now Q2 will only be 30, even in the case of 60, because 10 joule of energy is wasted due to irreversibility. This is totally wrong. Irreversibility does not affect the total energy. Energy is always conserved, it cannot be destroyed. But in case of Exergy, you cannot say that. In case of Exergy, There may be conservation of exergy, there may not be conservation of energy. Have we covered anything like conservation of available energy or conservation of exergy? No. What we have covered? Law of destruction of available energy, or law of that generation of available energy, that if everything is reversible, then no issue, no exergy will be destroyed, no entropy will be generated. But if process, system, cycle is irreversible, then entropy will be generated, exergy will be destroyed, available energy will be reduced. So there is nothing like law of conservation of exergy. You cannot say that. So if everything is going on reversible, in this case, and when everything is not going reversible, how this mathematics of available energy or exergy will hold, I will tell you that. Before, let me write it down that this is for energy. Okay, and before I start that discussion, let me ask you one thing very clearly, and I hope that maximum of you are able to answer it. Whether this heat engine is reversible or irreversible. Tell me how much is the available energy of Q2. The available energy of Q1, we know. Available energy of Q1 is that if a reversible heat engine is applied, is used between T1 and the minimum available temperature of T0, then what will be the work of that reversible engine? Because that will be the maximum work, and maximum work that can be extracted is nothing but the available energy, right? For this case, available energy is 70 joule, because it is the maximum work that reversible engine will produce from this heat coming from this temperature, right? But tell me, what is going to be the available energy of Q2? Q2 is rejected to lowest available temperature, T0. I have deliberately, knowingly not used T2 here. I could have used T1 and T2, but I have used T0 here to point out that this T0 is the surrounding ambient temperature. It is not any random temperature available higher than ambient temperature. It is the ambient temperature. So if a heat is going to ambient temperature, that heat ultimately will be having how much available energy. That is what I want to know. This heat which was available at T1, we know how to calculate its available energy. I am repeating it, I think for the third time, that using a reversible Carnot engine, using a Carnot engine or totally reversible engine, that work output will be its maximum available work. And this heat engine is to be installed between what temperatures? If I want to know available energy of Q1, whether I have T0 here or not, I just want to know that how much is the available energy of this heat. I don't know what is the whether I have T2 here or T0 here, but still, to find out the maximum work that I can extract from it, the available energy of Q1, I have to draw this diagram. I have to consider the lowest available temperature T0 here. Even if in this case, suppose I was having T2 here, I will come to that question, that what is the available energy of Q2. I will come to that, and this explanation will help you in understanding that. So suppose it was T2 here, and T2 is higher than T0. This is T0, which is even lower than T2. I want to know the available energy of Q1. What will I do? Will I use a reversible heat engine between T1 and T2? Or will I hypothetically use a reversible heat engine between T1 and T0? I have told this to you already, that I have to use T0. This is not the first time that I am telling you. You have to take the maximum temperature range available to you, right? And that includes the maximum temperature available to this heat and minimum temperature to which we can reject this heat. More will be the temperature difference, more will be the work that you can extract. And you want to know how much maximum work you can extract. So you have to take the maximum temperature limit for this heat only, right? Because we want to know the availability of this heat. So T1 has to come, and it can be rejected at the lowest temperature of T0. So T0 has to come. So between these two temperature limits, I will supply this heat Q1 to a reversible heat engine, to a Carnot heat engine, and that work output will give me how much is going to be the available energy, right? That available energy I already know. How? Because initially I told you that between T1 and T0, what work output you get? 70 joule. Between T1 and T0, I told you in this example that I get 70 joule of work. It means that availability of this heat is 70 joule. Whether in this case it is coming out to be 70 or not, it does not matter. In this case, I have T1 and T2. I don't have T0 here. I have T1 and T2. I want to know the available energy of this heat. Then I will not use a reversible heat engine between T1 and T2. I will use the reversible heat engine hypothetically, even if question has not given you that a reversible heat engine is to be used. Hypothetically, I will use a reversible heat engine between T1 and T0. And that reversible heat engine's work output will be available energy of this heat, even if in the actual situation heat transfer is not happening between T1 and T0, heat transfer is happening between T1 and T2, but available energy is not decided by the actual heat transfer happening. It is decided by the maximum possible heat transfer that can occur between the given temperature and the minimum temperature. So even for this case, obviously now we have T1 and T2 here. I don't have T0 here. So obviously I will not give 70 joule of work. Even if this is a reversible heat engine, the work output that I will get now will not be 70, because 70 joule I was getting when this was T0. That was the maximum possible value. I am using a higher temperature now. Obviously work output will decrease now. I have less temperature range available to me. In that temperature range I have to extract work. This will decrease now, right? But it does not change the availability of Q1. Availability of Q1 will not be decided by the actual temperature range between which heat transfer is happening, but by the hypothetically maximum possible temperature range between the given temperature and the lowest temperature. So even if some of you are having this confusion, because I have seen that many students keep asking such type of doubts, so I decided to explain this to you again and in a more detailed way. So this was in a way told to you earlier itself, but I told it again. And now let me ask the question. Tell me that, let me go back to the actual diagram. This was the actual diagram when heat was rejected to atmospheric temperature. Now tell me that in this case, how much will be the available energy of Q2? Tell me. It should be 0. The heat which is available at this reservoir, Q2 is the heat which is available at T0. Can you extract any work from that heat? Atmosphere is the minimum temperature available. The heat is available at T0, right? Don't think that this is the arrow, it is going from heat engine to T0. So between heat engine and T0 there is something happening. This is just a representation. Heat is directly lost to atmosphere. There is no gap between heat engine and T0, that heat is traveling via train through heat engine to T0. Heat engine rejects heat directly to the atmosphere. There is no gap or some medium between them. So whatever heat is rejected, this heat, it is directly available to T0. So at that temperature of T0 at which we are getting this heat, because earlier this heat is into the heat exchanger, and as this heat crosses the boundary of heat exchanger, we get it at T0. So if any of you have this confusion, that sir, this is how it is traveling, so how do you know Q2 is available at T0? Maybe Q2 is available in heat engine. So do we have to take that temperature with Q2 or this temperature with Q2? Maybe some of you can be confused in this. Don't be confused. Q2 is available at T0 only. You have the heat engine system. The heat is getting rejected. We already know the 4 components of heat engine. Heat is getting rejected directly to the atmosphere. So when the first time heat appears, it appears into the atmosphere directly. So if any of you were having this confusion, it should be cleared by this. So heat available is directly at the surrounding temperature. We have received the heat at the surrounding, which was rejected by the components of heat engine. Now tell me, this heat is directly rejected to the surrounding. Can you extract any work from this? No, because it is available at the lowest possible temperature. T0 is the lowest possible temperature. If you want to know the availability of Q2, which is in the atmosphere, this is the heat engine, it rejected heat to the atmosphere. Now it is available to me in the atmosphere. How can I find out its available energy? By hypothetically connecting this reservoir, this ambient temperature, with the ambient temperature. Now it automatically is the ambient temperature. You don't have a lower temperature available with it. So even hypothetically also you cannot have any interaction, heat interaction or work generation between T naught and T naught. Both of them are same temperature. Why heat is going to flow between them? Once heat has reached the ambient temperature, it's gone now. You cannot extract any work from it. It is already at the minimum available temperature. To extract heat, to extract work, you need heat transfer. And for heat transfer, you need temperature difference. This heat is already at minimum temperature. You cannot have any heat transfer and any work extraction, even not hypothetically. That is why the heat, the available energy of this heat is always going to be zero. The availability of Q2 is zero always when rejected to ambient temperature. The point is that Q2, the available energy, it will always be zero when it is rejected to ambient temperature. Its value may change. The value of Q2 may change depending upon reversibility or irreversibility of heat engine. But availability of Q2, the exergy of Q2, how much work you can extract from Q2, that will always be zero if it is rejected to the ambient temperature. Now coming back to the initial discussion. The initial discussion that I was doing was this expression, whether this conservation of energy funda you can apply for available energy also, for exergy also. Look, if this heat engine is reversible, this is T1 and T0, okay? If this heat engine is reversible, you will get the maximum possible work because it is between T1 and T0. This 70 joule is the available energy or exergy of Q1, right or not? Q1, irrespective of whether this is T0 or T2, will have available energy of 70 joule. I told you this temperature can be any temperature. For available energy, I will hypothetically assume heat transfer between the maximum available temperature of Q1 and the minimum available temperature. So Q1's available energy is fixed. Its available energy is 70 joule. Whether this heat engine is, in actual case I am telling you, is reversible or irreversible, whether it is T0 or T2, it does not depend. Available energy, I have told you via formula also, it depends upon the amount of heat Q, it depends upon the maximum and minimum temperature T1 and T0, right? These are the two things in which the temperature range and how much heat, on which maximum work that can be extracted depends. And obviously for maximum work, I will hypothetically assume a reversible heat engine, even if in reality there is a irreversible heat engine. True? So available energy is not going to get affected by this or by this, because this is determined hypothetically. But suppose this is a reversible heat engine, okay? In reality also this is a reversible heat engine. What will happen in that case? Obviously work out will also be 70 in that case, right? Tell me how much is the availability of this work output. Availability of work is equal to work itself. What is availability or available energy? That how much work can be taken from that energy, from that heat, right? If I want to know how much work I can take from the work, then what kind of question is that? It is work itself directly. You are getting the work. So exergy of work is equal to work itself. How much work can you get from W out? 70 joule equal to W out itself, because already it is work. So how much available energy you are supplying to heat engine? 70 joule, right? How much available energy heat engine is rejecting or giving you? 70 joule. How much available energy does Q2 has? 0. So if for this case, for reversible heat engine, I want to write, I can very much write that available energy 1, this is AE1, let's say, this is AE2. So available energy 1, which was supplied to heat engine, is equal to the work out, which is also available energy out. You can say this is available energy out or work out, plus available energy 2. Why? Because available energy 2 is 0. So 70 is equal to 70 plus 0. This is coming out to be true. The available energy looks like it is also conserved, right? But it's not true. Now consider the case of irreversible heat engine. When this heat engine is irreversible. Now in this case, tell me how much work you will get. 70 joule of work you were getting when heat engine was reversible. But now when I have irreversible heat engine, this work of 70 joule will be less. Let's say this is 60 joule of work. Right? So how much is the available energy out that you are getting? 60 joule. Is it changing the available energy of 1? Is AE1 getting changed whether it is irreversible or reversible heat engine? No. I have already told you, I think 3 times, 4 times, a lot of times, because beginners can take time to understand this. That is why I repeated that thing. But I have told you that this available energy is hypothetical between T1 and minimum possible temperature T0. Even if this is T0 or T3 or T2 does not matter. This is not going to change. This is hypothetical between maximum and minimum temperature with a reversible heat engine. In reality, whether you have reversible heat engine here, you have T2, T3, T4, T10 here, does not matter. So this value is not going to change. Right? It is related with Q and the maximum available temperature difference to you. Clear? This available energy is 60. Directly, how much work you are getting is 60. You are not getting 70 work here because it is not a reversible heat engine. It is irreversible. Work out will be less than the 70, than the maximum value, right? Interestingly, this also will be having a 0 available energy. Why? I have told you that this heat which is available at minimum temperature has 0 available energy. It is available already at the minimum temperature. How you can extract heat from it by using an even lower temperature? Not possible. Now in this case, if I try to do the mathematics, AE1, which is 70, is equal to AE out plus AE2. Is this expression going to be true? This is 70 is equal to 60 plus 0. Obviously not true. This is not true. This is not equal to the available energy it receives is not equal to available energy it rejected. So where has the available energy gone? It has been destroyed because this is an irreversible heat engine. And unlike energy, Exergy can be destroyed. Available energy can be destroyed. You cannot say that where it has gone, no, I want my available energy back. Please give me the available energy. He will say it is gone, destroyed. I cannot give it back. Right? So this funda of conservation of energy you cannot use for available energy for Exergy. Is that clear? Yes. If things are totally reversible, in that case you can say that it is going to be conserved. But can you say it as a general expression? No. I cannot say it as a general expression. General expression can be said only when it happens all the time. Every time if something happens, only then you can call it as a general expression. Otherwise, if a statement is asked to you in the exam that is the Exergy or available energy conserved, then don't think that yes sir it is conserved for reversible case. It as a general statement you cannot say it is correct because it is not true for all the cases. Only for reversible cases it is true, right? Which we know are extremely rare in the real life situation. As a general statement you cannot say, but yes, if a question comes in which cases you can use it, the available energy conservation concept, then only for the reversible cases. So in this whole process, if I ask you how much available energy has been destroyed, how much available energy has been destroyed? 10 joule. 70 joule it received, 60 joule it gave. 10 joule is, I don't know where it has gone because it has destroyed, right? And now if I ask you, suppose for the same question I am asking you, tell me the entropy generated. How much entropy is generated? It is very much obvious that if this process is irreversible, entropy is getting generated. If entropy generation was 0, then process was reversible. And we can use that expression, that irreversibility, or you can write it in so many ways, irreversibility or loss of available energy or destruction of available energy. Everything is irreversibility. If there is zero irreversibility, there is no loss of exergy, right? So irreversibility, as we know, is equal to T naught S gen, right? How much is the irreversibility for this case? 10 joule is the irreversibility. Irreversibility tells you how much energy has been, how much available energy has been destroyed as a result of irreversible things, irreversible processes, irreversible systems. Destruction of that is 10 joule. T naught, we already know, it will be given to you if a question comes like this. And using that, you can find out S generation by 10 divided by T naught in Kelvin. Right or not?